Loop means it does a full 360 circle, and then it just goes out like that. So if you are in this roller coaster, it'll go like this, like that, and go like this. Okay. Now this roller coaster will be at the bottom of this circle here. So that's this scenario. It will be doing an upside down here. That is that scenario. Okay, so these are the two. But then the roller coaster continues here, and it goes over a part of a track that looks like this. So in that case, where would the roller coaster be here? So it does that and then goes over the top like that, right? And then eventually there's a part of the roller coaster here that is inverted, as in like that. So the roller coaster will eventually go upside down. Okay, so that's the whole track. Is it possible? Is it not possible? We'll see in a bit, but this is basically the track. Okay, so clarify. Yep, this is the track of our roller coaster. We need to figure out by doing math if circular motion is possible or not. Now I have to clarify something. The roller coaster we are discussing here is called free-form roller coaster. So what's a free-form roller coaster? It's essentially a roller coaster where the roller coaster is not attached to the track. Now, I know you probably have seen roller coasters where people hang upside down, right? Those roller coasters, the vehicle, right, is actually connected to the track. And the people in the vehicle are attached to the belt. So they're actually stuck to the track, right? But this is not that. This is free form. It's not a roller coaster. Have you seen those toy cars that have tracks out there? Hot Wheels, right? We can get into the car, will do like a free form circle on its own. It's not attached to the track. This is what we're doing right now, okay? Because if you include the forces applied by the track, it becomes different. Then circular motion actually is not working naturally. So yeah, this is the scenario out there. The first thing that we'll do today is try to figure out what are the forces acting here and how is circular motion attained here. So can you tell me for the first scenario, what are the forces acting on the object? We'll first label just the forces. Weight, right? So weight is acting downwards here. And that's the case with all of them. So there's weight acting on each scenario provided here. So there's weight acting downwards here, weight acting downwards there, and weight acting downwards there. Is that clear so far? Now, can you tell me what is the direction of the reaction force? Upwards, right? So in this scenario, where is reaction force acting? The first one, upwards. Why is it upwards? Why is reaction upwards here and not downwards? Right. So reaction force is always against contact. So if you're like touching this table like that, reaction will be which way? Upwards. If I take this and touch it to the ceiling, which would reaction be? Downwards. It always opposes your contact. And why is that so? Why is reaction force always opposing your contact? So let's say this is a ceiling, and this is a part of physics that we need for our questions Arjuna Karachi. So this is a ceiling here, and let's say you push an object or you hold an object against the ceiling, okay, with your hand. So which way is weight acting downwards? Which way would reaction force act? Will it be upwards or downwards? Downwards, right? Because there's a common misconception out there that reaction force always acts opposite to weight. That's not true. So in this case, the reaction force will also act downwards. Can anyone explain the logic behind it? Why? Like the science behind it. Why is the reaction force acting downwards? Right. It's the reaction is the reaction to what's keeping it up. Yes. So the science behind this, let me explain, is do you guys know what's the origin of your contact force? Where does it start from? What provides reaction force? No, that's the law that says that there must be reaction force. But I'm asking, like, when an object is in contact with a surface, it experiences a force, right? Called the normal reaction force, contact force. Why is that force there? Friction. Sorry. No. What is that force? Acha, I mean to clarify, this is like very fundamental. So if you don't understand this, it's a problem of it. This is a surface here, right? And I place, let's say, the remote on the table here, right? This will experience a downward force. What is that? Weight. But isn't there an upward force here? What do we call that force? Reaction. Why does reaction exist? That's my question. If you say it's because this is pushing it down, that's not the answer. There's another reason for it. Why does reaction force exist? That is the consequence of reaction actually existing. But my question is that why is the reaction force showing up? So when I pick it up in the air, is there reaction force? No, right? The moment I keep it on the surface, there's a reaction force. So it originates from the surface. My question is, who provides that force? The surface. What's in the surface? You're right. Okay. So the correct answer is this is actually maybe leveler একটা জিনিস, but I want you to understand this because এখানে আজকে it might make more sense. So reaction force is actually electrostatic repulsion. And the reason for reaction force is that when you have two surfaces next to each other, both surfaces have what in their outer layers? Electrons. This is inevitable. There is no possible scenario where you will have an object with no electrons in the outer surface. And this is negative and this is negative. When you bring them very close to each other, right, the electrons on the surface will what the electrons on the object? Repel, right? So the closer you come, the more that repulsion is. And eventually that repulsion is equal to the weight that you're provided, because that's the downward force you're providing. So the electrons will provide what force upwards? Equal and opposite. Okay. So if I take this remote, right, and keep it on the table, and now the reaction force is equal to what? Weight, right? Because that's the force applied. What if I press down on it? Will the reaction force still be same or will it be higher? Higher, right? Why is it higher? Because now I'm applying more force, so the electrons apply as a reaction more force back on me, right? So that's why reaction is literally how much force the object is applying on the surface electrons, and the surface electrons will provide what force back? Equal and opposite, right? So if you look at this scenario here, this is the trolley, and the trolley is applying a downward force on the surface here. So what happens is the surface provides an equal and upward force on the trolley, and that force is what we label as reaction force, right? So can you tell me what is reaction force for, or what's the reaction force in this scenario? Upwards or downwards? How many of you think the reaction force here is going to be upwards? It's supposed to be downwards. Because the trolley is trying to push the road which way? Outwards. Isn't the trolley trying to fly out? And then who brings it back in? Centripetal force, right? So as it tries to push itself out, right, it's pushing on the wall at the top. As it pushes on the wall on the top, what does the wall do? Push it back down, right? Now students will argue, then why doesn't it fall? Because all the forces are acting down, right? Why doesn't it fall? It falls. It will fall, right? But if you go fast enough, you may overcome the rate of fall, and eventually you'll become what? Part of a circular motion. A best example of this is called the daredevil cage. You know what that is? It's basically a cage in which bikers just go in circles, in like circus or other places, right? So the bikers can go full 360 and come down, right? There is actually a video out there on internet where a car does that. But you have to be what in order to be able to do that? Fast, very fast. You have to be faster than gravity can bring you down. You get my point? So when you're at the top, and if you're very fast, before the gravity can bring you down, you cover that point and come downwards. So it only happens when you're fast enough. Okay. So anyways, reaction force is acting downwards here. And for this scenario, can you tell me which way is reaction force acting? Upwards, right? Very good, because the contact is downwards, right? So reaction force is upwards. And in this scenario, which way is reaction force acting? Downwards. Downwards, because contact niche dike. So yeah, these are the forces acting here. And those who join later, I mean, to explain what we're doing right now, we're trying to see how roller coasters work. Keep in mind, the roller coasters we are dealing with here are free-form roller coasters, which means that they're not connected to the roller coaster. They're like free to move around. Because if you think of real roller coasters out there, they're all attached to the track, the cabin. Why? Because what if it goes upside down and then something happens and it stops, right? Wouldn't it be a safety hazard? So they're actually attached to the track, so they can stay upside down like that. And the people inside the cabin are actually attached with like belts and whatnot, right? So that's the roller coaster that you probably will actually experience. This is not that. This is very dangerous. If you're not at the right speed, what will this do? Crash. Okay, it's just like testing your luck here. Like if you're at the right speed, you'll do a circle. If you're not at the right speed, it'll just go at the top and the whole thing will collapse. I'll show you animations of it, how it happens. Okay. So, anyways, now we're doing circular motion. So, can anyone tell me for the first scenario, the centripetal force? By the way, if you're wondering where is the center of the circle, that's the center of the circle, that's the center, that's the center, that's the center. So in the first scenario, can you tell me what provides my centripetal force? Weight. Is it just weight or is it weight minus R? Yeah, because the idea was for circular motion to happen, you must have a what force acting towards the center, resultant, right? So that's going to be W minus R. So that's that scenario. Can you tell me what's the scenario for the one here? W plus R, correct? W plus R. And what about this one? R minus W. Do you see parallels to this with the vertical circular motion where the rope had tension and weight? Okay, fine. Can you tell me what's the centripetal force here? Minus of W, which means it's not towards the center. R plus W, it can't be R plus W, right? Because that's my center and the weight and the reaction are the other way. I need a force to act towards the center for circular motion. So what should it be? Huh? Exactly, that's the correct answer. It's impossible. So there's no roller coaster on Earth that can actually do this on its own. Okay, but if the roller coaster is attached to like things on the track, then this is very common. This is actually a very common part of roller coasters. Okay, but there's no roller coaster that can do this upside down motion, regardless of whatever speed you're sending it. Right? Who's there to bring it back in? No one. Okay, as a result, it can't. But the typical roller coasters, they can come back in because who has force applying there? Tension. The track applies tension and it holds it in its place. Okay, so yeah, these are the ones. So yeah, I hope you understand that out of the four here, only one is not possible. The rest of them are actually realistic. They can happen. So we'll be doing math based on this, and yeah. So just copy whatever you want. You can take it, start the scenario, and then I'll give you a question to try out. There's a blank page of roller coasters. You can add it there. No, reaction force is contact force. What have you lost? Calculator. Last class. No, I don't think it'll survive like the classes between. Done? Okay, I'll give you a question to try out. Okay, a roller coaster is released from a height of 400 meters and undergoes a circular loop motion of radius 100 meters. Find if it makes the loop or fails. So let me explain what the scenario is. So you have a roller coaster that starts from 400-meter height. So you'll find that roller coasters, when they start, they have to be raised to a height, right? Like, there's a machine that takes them to the top, and that makes them gain what energy? GP, and then they're released, and the GP becomes K, right? So it goes to the top like that, 400 meters up, and then it comes down here, and as it reaches the bottom here, it enters a loop. So that's the circle that we're looking for. Okay, so what you need to figure out is, does it make the loop or does it fall? Now, what does that even mean? I'll show you an animation to explain. Okay, so this is the roller coaster. It's very basic, right? So let's see what it means. What is this circle here? Okay, look at this. It's an interesting setup here. So there are a few parameters that I can change here. Can you see at the bottom? It says mass of the coaster. I can change the height of the hill. So, I can make it lower or higher, right? I can change the loop radius. So there's a loop on the other side, right? I can make the coaster smaller or bigger, right? So these are different options out there. So let's try this one. So what I'll do is I'll use a coaster of 3,500 kilogram mass. The hill where it goes is 60 meters, and the radius of the loop is 80 meters. See what happens. So it gains energy here, and then it goes down. These are the forces acting here, right? So it manages that, and it fails, right? Why did it fail? Very obvious. This is like an O-level question. Why did it fail? Not enough GP, right? Because it didn't have enough KE. So আমার যদি 40 meter পর্যন্ত race করা হয়, ছাড়া হয়, how is it going to go all the way up to 60? Energy conservation is, a mandatory thing, right? So it has to first obey that. So my hill has to be what than the circle? Higher. Otherwise, it shouldn't work, right? Let's try now. So I have given it enough energy to be able to go up, and it goes down like that. And yes, it does that very well, and it fails. Okay, so why did it fail? And that's what you're going to do right now. So the question I've given you is to figure out, does it fail or does it succeed? How can I make this succeed? What do you guys think? Lower in the mass. And what? Lower in the loop. Smaller loop. So there's less mass here. And this is fine. Nothing happens at the bottom. Okay. And it's successful. And then it goes here, but then it flies. So we learned this last class. Why did it fly? The reaction became zero. You see the reaction arrow wasn't there. So if reaction is not there, what does it do? It flies, right? So to design a proper roller coaster is very complicated. Yeah. So if because then it'll provide more centrifugal force, right? So let's see. So yeah, this will do fine here as always, and it does fine there as well. And no, it flies again. So yeah, it's a little difficult to design it eventually. Okay, but yeah, আমাদের তো এটা ডিজাইন করতে হচ্ছে না, আমাদের just বের করতে হবে, does the roller coaster survive this loop? Okay, so loop the key information দেওয়া. It starts from a height of how much? 400 meters, and it goes to a circle that has a radius of 100 meters. So the radius is 100 meters, and you need to figure out, does the roller coaster survive this circular motion? Can it manage it or not? Now, before you start, what would you look for? The weight of the object, and you compare that with what? By the way, weight is 100 kilogram. This is the weight of my trolley. So yeah, how would you find out whether it makes a successful loop or not? Yeah, you're right. So you first find the GP, and then you find the KE, and then you find the velocity. Very good. And then that's the first step. Okay, somehow you have to find the velocity of the trolley at the top, because the velocity is an important factor. Okay, Tarpur? Yes. Okay, so yeah, remember we just found an equation for the upside down proportion. What was the equation for upside down? Fc equals to W plus R. What you're gonna do right now is find the value of R or Fc, either one of them. If your R is a positive number, listen carefully, okay? If your R is a positive number, what is the roller coaster doing? It's in contact. If your R is 0, what is the roller coaster doing? It's supposed to fly. If your R is negative, what does it mean? It's already fallen down, right? So it never makes the top. So the only way you can confirm if your roller coaster is part of the track is that if there's what value available, positive R value. So you have to do the math and find out what the reaction is at the top. If the reaction is a negative number, it means it has fallen. If the reaction is 0 exactly, it means it's barely there. Okay, because now weight is taken over. And if it's a negative, positive value, it means it's sticking to the surface. Okay, so try karo. It's 5 marks. It's one question. Okay, so there's a bit of work that you need to do. All right, reaction. You found out. Oh, you can find FC. What's centripetal force formula? No, the original formula for centripetal force. M omega square R or M P square by R. So if I could find the velocity of my trolley at the topmost point, right, I would be able to find FC, and I also know weight. And then I can find R. It doesn't fail. You got a positive reaction. How much do you get? I don't think that's the answer. It doesn't fail, that's true, but I think the reaction is a little different. Yeah, put it up here. So these are your tools for circular motion. Okay, if you can remember them, then you'll have trouble solving any question from this chapter. I'll put it up here. I'll bring it up every time we do questions so that you can remember. So yeah, these are the 4 equations that help you solve any circular motion question out there. The one we'll be using is number 4, centripetal force. 6.8. Did you get same? 6.8, 6.7. 890. Okay, so those who got answers, what do you think? Does this succeed or fail? Yeah, because there's a very positive value out there, which means it's sticking to the surface. Okay, step by step, Corey. First thing that I want you guys to find out is what's the speed of your trolley at the top? 88 point. How do you find that? GP equals to KE, right? So what's the GP value? MGH. What's the height? No. If you use 400, that's the speed at the bottom. But as it goes up, doesn't it lose GP? Wait, you guys didn't get what I said? Look at this. If you drop something from 400, right? So it'll lose all the GP and it'll become KE at the bottom. But then if it goes back up again, doesn't it lose some K and gain some GP? So would the speed be the same throughout or will it decrease? Yeah, it should be lower, right? That's the problem. So maybe the 88 point something. That's the speed at the bottom of the loop. But as it goes up, it's on its own, right? So it has to use gravity's GP to become like raise itself, right? So it's going to lose some energy. So it'll slow down at the top. Oh, no wonder it's only at the border reaction that's slow. That's very high velocity. Around 3000. Yeah. 2943. Yeah, that's the answer. Kiyash velocity at the top. What's the velocity at the top? 60. Correct. It's a খুবই elementary mistake করছো তোমরা. How did you assume that the velocity at the bottom would be the same at the top? And doesn't it lose energy to get to the top? So it should slow down, right? Do you know that if this loop was 400 meters in height, as it went to the top, what would the velocity be? 0, because all lost GP is gained back as K, right? So then all K is gone back to GP. But এটা তো এখানে এই পয়েন্টে velocity বের করতে হবে। আচ্ছা আমি করে দিই। So the way you do this, I'll do the first part, which is find the velocity at the top. So what you do is there's a shortcut grade 9 এ করি এটা আমরা, that if you have change in velocity, right, or you need to find the energy, you need to just take the net change. So the object falls 400, but it rises up how much? 200, right? Because that's the total height here. So what is the net loss in GP here? It's only the one at the top, just that much, right? So how much is that? 200, right? So the net GP loss is this one here, which is net height change, 200 meters. And you need to find the energy based on that 200 meters. So for that, what do we do here? First step is change in GP equals to gain in K. How much is the net change in GP? mg, what's my height here? 200, that's the change, right? Equals to K is half mv square. So that will give you the velocity at the top of the loop. It's 60, 62 point. Oh, sorry, weight net of mass. It should be mass. I get kilogram, right? Right. So what should the velocity be? 60? 62.6. 62.6 meter per second. But the thing is, even if you did mass or weight, right, answer same because they cancel out, right? So even if you took wrong mass value, velocity shouldn't change. But anyways, 62.6 meter per second is the velocity. Now I need to find what first? The centripetal force at the top, okay? So at A, let's call it A. At A, what is my centripetal force? What's the formula for centripetal force? M omega square R or mv squared by R? What's omega? Angular speed, right? Do you know that? No. In this question, we don't know angular speed. Angular speed is a rate of rotation. We don't know that, right? Do you know the actual tangential velocity? Yes, that's the actual speed obtained by the object, right? So that is v. So mv squared by r is viable here. So that's 100 into 62.6 square divided by, what is the radius here? 100. How much is this? 3924 Newton. So to screen it, the centripetal force requirement is 3924. Who has to provide that? Weight and reaction, right? So let's see. So if I apply the forces, so equation at top, equation at A. What's the equation at A? Fc should be equal to what? W plus R. So I know my centripetal force, which is 3924. I know the weight, which is 100 into 9.81 plus R. And as I do my math here, I find that the reaction force is how much? 2,900, right? 2,943 Newton. It's a positive value. So since it's a positive value, what does it mean? The trolley is in contact. Hence, it makes the loop. That's the answer, okay? Does it make sense? শেষে গিয়ে আচ্ছা এদিকে গিয়ে ওইটা হ্যাঁ ওইটা হচ্ছে বেসিক্যালি ট্যানজেনশিয়াল ভেলোসিটি আগে নিয়ে গেছে ওকে ওই মোমেন্টে পড়ে নাই আর যদি স্পিড অনেক স্লো হয় ওইটা আগে পড়ে যাবে in a side of the loop. Yes, it is possible. Oh, the reaction would definitely be 0 and less. So it could be a negative value. If it's a negative value that shows up earlier, it already lost contact before. And if a negative value shows up later on, it loses contact later on. So it depends on when the negative value showed up. K would, yeah. So it'll just do this and it's slowing down, and then does like a very quick fall like that. So gravity will bring it down. So it'll become faster as it goes down. And when it reaches the bottom, you'll find that velocity that everyone found earlier, 88 point something, because whatever GP is lost, it's come back again as KE. Downwards, right? When it's upside down, the trolley is pushing the wall upwards, so the wall pushes the trolley downwards. Yeah, I think we are done with all the examples out there. There is this one that comes from the next chapter, but I think right now we are capable of solving it. So it probably we're done with all types of questions out there. Ready to try, Kuro. This one is a very interesting question. It's about how weighing machines don't show your right weight at all. Okay, look at this. It says that weighing machine weight reading when a person standing on the machine at the equator and at the pole. So mass of the person is provided, radius of the earth is provided. At first glance, sometimes students don't even know why is this the question. Like, you know, you're on a weighing machine. Weighing machine is at the equator, it's at the pole. Apparently, your reading of weight would be different. Why is that so? Isn't your mass the same? So why is it different? Is gravity changing? No. So why is it different? So we'll see right now. So imagine this is the simplified version. The person who's at the equator is standing on the weighing machine right at the equator like that, right? So this is the simplified version. And the same person will now be standing on the weighing machine at the pole. So it's like that. You need to find out what the readings on the weighing machine would be when you are at the equator and you are at the pole. Okay. So find it. You may feel it's unfair, but this is the exact past paper question. Okay, like, word to word. I didn't change anything. It's just the question came in gravitational field chapter, though it has nothing to do with gravitational fields. It's to do with circular motion. That's why I gave it here. Okay, so I'll give you a hint. দেখে মনে হচ্ছে কিছু start হচ্ছে না. So hint number 1. Which person is undergoing circular motion? The person at the equator or the person at the pole? The Earth is moving. Right. So is the person at the pole undergoing circular motion, or is the person at the equator, or both, or neither? Yeah, the person at the equator. The person at the equator is undergoing like a massive circular motion because it's the biggest circle out there, right? The person at the pole is not really undergoing circular motion. The person at the pole is basically the person at the watt of a fan, center of a fan. Remember, I said you can touch the center of any fan out there, regardless of how fast they're spinning, right? So the person at the pole is moving. He's moving at a point and just swiveling around the point, not really going in a circle. Okay, so is the person getting any displacement there? No, but the person at the equator has been displaced maximum at angle, right? So he undergo the greatest circular motion out there. So as you start to move from here, so the circles are like this. Okay, that's how the circles look like. So that's why the person who's at the equator would have the greatest circle. The person who's right at the pole is not really undergoing circular motion because he's right at the center of the circle. Okay, so yeah, that's the only hint you would need. Rest far about that. Which one? The circles. Acha. Have you seen people, they can spin like a basketball on their finger, right? So when they spin the basketball on the finger, right, the finger is at the point. Is that point moving around in a circle, or is it fixed? Fixed, right? But the edge of the basketball, isn't it going in a circle? So somebody who's at the point of rotation is not really undergoing circular motion. But the person who's going fully around is undergoing the greatest circular motion. So that's the equator and the pole. Is in the first symbol. No, that we don't, but that you need, and that is not given. There are both any questions. Yes, so in order to be able to answer this question, you need to know how fast the Earth is spinning, which is an information that's not provided in any place in your question paper. And it is an information that is not purposely provided in this question as well. There's a way you can find it. Yes, very good. By T and the omega. Yes, that's very good. That's how you do it. You'll find omega. The person is spinning around this center, right? So anyone who's spinning here is going around this. So it's like that. But this person is just fixed like that. For the Earth. I think so. What is it? You don't know. What 24 hours? It takes 24 hours for the Earth to do one cycle. What do you think? What do you call that thing when the Earth does one rotation on its own axis? It's called a day. The weight. Count how much was 70 mass, right? So by default, the weight 70 pounds of it. 70 into 9.81. Negative. The force, centripetal force. Yeah, that's correct. But centripetal force is not what you see on the scale. The scale doesn't show centripetal force. Also, yes, I forgot to remind you of this, something you learned in O levels. When you have a balance like this, right, and then it shows weight, like you take this and you place it here for mass, right? The reading that you have on the balance, is it the weight? It's a reaction, right? Because I can press it and it changes. So it's not really the weight of the object, it's actually the reaction. So the weighing machine always shows the watt of a person, reaction. And that's why you have the questions in your AS with the lift. If you're in a lift and the lift is moving, aren't the readings on the scale changing? So the scale will always show reaction force, okay? Acha Koride, ready? Is there anyone who wants to share their answer? I'll start. 10 to the power. The reading on the scale. 10 to the power 13. That's like heavier than planets. 600? Yeah, that's the answer. Okay. আচ্ছা সবাই স্ক্রিন আমি করে দেই একটু বুঝো কি হচ্ছে don't write anything, see what's happening here. So you have a person on the weighing machine here, and this is at the equator. And at the equator, the person is undergoing circular motion like everyone else. And there's a force acting downwards on this person. What is that? What is the downward force? Weight, right? Okay, fine. And by the way, this is the diagram sideways. Sorry. This is basically this diagram sideways, okay? So yeah, this is the direction of weight out here. Now, for this person to successfully be in a circle, the weight must be providing your what force? Centripetal force, right? So can you tell me an equation here in terms of weight and reaction so that centripetal force acts which way? Downwards. Ki korba? It's a very simple exercise. I need a net force acting downwards. Whenever there's circular motion, right? There must be a what force acting towards the center, a resultant. In this question, there's W acting downwards and R acting upwards. How can you arrange the values so that the resultant is downwards? Right. So FC must be equal to W minus R. And what does R represent here? Reaction force. And that also represents the what? The region of the scale. Very good. So R is going to be W minus FC. So that's what you need to find out. But the problem is we do not know what FC is. So let's first find FC. FC equals to M omega square R. Mass of the person is 70. What is omega, the angular velocity of the person? It's 2 pi by T. Remember the formula? So 2 pi divided by T is time period. Time period for the person to go in a one complete cycle, which we refer as 1 day. So that's going to be 3600 into 24 square. And what we do next is radius 6400 into 10 to the power 3 because it's in kilometer. Can you tell me what's your centripetal force? 2.3637. Okay. So here's the thing: a person at the equator requires how much force acting on him to keep him in on the surface of the Earth? 2.37. If the person's weight happens to be less than this, right, the person will fly off. Okay, but luckily the weight is much higher than this, so it never happens. So that's my centripetal force. So if I place the value here, weighted formula ki hobe mg, 70 into 9.81 minus what is centripetal force here? 2.37. So what is the reaction force that a person sees on the scale at the equator? 684.3 Newton. Now I'll teach you something here. So are you okay with this much? Can you tell me what's the reading on the weighing machine at the pole? R equals to W, because what's the centripetal force needed for the person standing at the pole? 0. Why is it 0? Because the radius is 0. Okay, so what should that be? 70 into 9.81. That's the actual weight of the person. 680, 86.7. Acha. There's this, science fact that's thrown around sometimes, which is that you weigh different at different parts of the Earth. And they say that that's because of the what of the Earth? Shape of the Earth. And they say that the shape of the Earth is a little bulged. It's like at the top, little squeezed and wide at the center. That has nothing to do with the value of G. The reason why your weight is different is due to what actually? Circular motion of the Earth. So yeah, grade 9 but 10 that a person's weight is different at the equator and at the poles. And they don't say why. And students then start to think, oh, that's because the Earth is like squashed. Then gravity is different. No, gravity is based on all the mass. Okay, not masses this way and that way. So why is it actually different? It's because the spin of the Earth. Okay, so that's the reason. Yes, it is different. The actual value you see on a scale. Okay, but is your weight actually different though? No, it's just the reading on the scale that's different, and the reading on the scale is reaction. So the weight is actually the same, because see, what was the value here? 9.81. What did we use here as well? 9.81. It's just the interaction with the weighing machine that gives you like a lower value. Okay. Also, it's so low that you wouldn't really notice. So it's not like you're actually lighter. So reading J decimal places show for it, that doesn't show up in a weight scale. But why would you take your weight to 4 significant figures? No one does that, right? So anyways, that's the answer. So this is the reading at the equator, that's the reading at the poles. So yeah, we're done with circular motion. On our next class, we'll do questions from the past paper, and if time permits, we'll start gravitational fields. That's our next chapter. I'll upload these in Google Classroom today. Okay, so if you have missed anything, you just update that.